In this session, we are going to see the universal gates in detail. So, the universal gates are NAND and NOR gates, and why they are known as universal gates? Because we can implement any logic functions or any other logic gates using only NAND gates and using only NOR gates. So, now we are going to see how to implement other logic gates using only NAND gates and only NOR gates. So, first we will see about NAND gate. In that, the first one is NOT gate. That means we are going to see how to implement NOT gate using only NAND gate. So this is the circuit diagram of NOT gate using NAND gate. It is very simple. We are shorting the inputs of a two input NAND gate and giving a single input A. And what is NOT gate operation? Output should be inverted of input. So input is A. We want to get A bar at the output. For that, what is a NAND gate operation? A dot B the whole bar. Here there is no B, both the inputs are same A. So the output will be A dot A the whole bar. A dot A the whole bar. What is A dot A? A dot A is A. So A bar. So Y is equal to A bar. That only we want for the NOT gate. So this is the circuit diagram of NOT gate using NAND gate. Now we are going to see how to implement AND gate using NAND gates. So this is the circuit diagram of AND gate using NAND gates. Two NAND gates we are using here. To the first NAND gate we are giving two inputs A and B, and the output of this first NAND gate is given to the second NAND gate whose inputs are shorted. If the inputs are shorted, this is going to work as a NOT gate that we already discussed. So inputs are A and B here to the first NAND gate. So the output will be A dot B the whole bar. Now A dot B complement is given to this NAND gate with input shorted, which is working as a NOT gate. So the output will be A dot B complement the whole complement. And we know that A complement the whole complement is A. So here A dot B complement the whole complement will be same as A dot B. And this is the operation of AND gate. So we are getting AND gate operation using NAND gates. Now the next one is OR gate using NAND gates. So this is the circuit diagram of OR gate using NAND gates. Three NAND gates we are using here. So here the first NAND gate inputs are shorted and giving the first input A. This is the second NAND gate, again inputs are shorted and giving the second input B. Now the outputs of first and second NAND gates are given to this third NAND gate. Now if the inputs are shorted, this is going to work as NOT gate. So if the input is A, output is going to be A bar. Now here the input is B, output is going to be B bar. Now A bar and B bar are the inputs to this NAND gate, and NAND gate operation is what? Multiplication and then complement. Here the inputs are A bar and B bar, so the output will be A bar into B bar the whole bar. That is the operation of NAND gate. Now we will see by applying De Morgan's theorem. What is De Morgan's theorem? A dot B the whole bar is equal to A bar plus B bar. Now what is A bar? A is A bar. So A bar will be A bar the whole bar plus B is here, actually it is B bar. So B bar will be B bar the whole bar. So B bar the whole bar. Now A bar the whole bar is A, B bar the whole bar is B. So what will get at the output? A plus B. A plus B operation is nothing but the operation of OR gate. So we are getting OR gate using the NAND gates. Now the next gate is NOR gate. That means we want NOR gate using NAND gates. So here we studied OR gate using NAND gates and how we can relate OR gate and NOR gate. NOR gate is actually OR gate plus NOT gate. So here till here it is OR gate, and output of OR gate we are connecting to one NOT gate, and NOT gate using NAND gate. So the entire circuit will act as NOR gate. That means till here it is OR gate using NAND gate. OR gate using NAND gate is connected to one NOT gate using NAND gate. So this is OR plus NOT, which is nothing but the NOR gate. Next is XOR gate using NAND gates. So this is the circuit diagram of XOR gate using the NAND gates. Now we will try to derive the output of this circuit, which should be same as the XOR gate operation. XOR gate operation is what? A bar B plus A B bar. Now we will see the circuit step by step. A input is given to this first NAND gate and also to the second NAND gate, and B input is also given to the first and this third NAND gate. So here the output of this first NAND gate will be inputs are A and B, so the output will be A dot B the whole bar. Now this A dot B the whole bar is one of the inputs to this first, second and third NAND gates. So here one input is A and the other input is A dot B the whole bar. So the output will be what? Multiplication and then complement. One input is A second input is A dot B the whole bar. So A dot B the whole bar and the whole complement. So this is the output of this NAND gate, which is same as, again we are applying the De Morgan's theorem. What is De Morgan's theorem? A dot B the whole bar is equal to A bar plus B bar. Here A is A and B we are taking it as A dot B the whole bar. So A bar, what is A bar? A complement. We are getting same A complement plus, here B is what? A dot B the whole bar. So A dot B the whole bar will be A dot B. So the output of this NAND gate will be A bar plus A dot B. Same way, output of this NAND gate will be B bar plus A dot B. Now these two are the inputs to this NAND gate. Output of this NAND gate will be what? Multiplication of these two inputs and then the complement. So multiplication of these two inputs mean first input is A bar plus A dot B into B bar plus A dot B the whole bar. This is the output we are getting. Now we are going to simplify this using the De Morgan's theorem. So this entire term we are going to consider it as a single term A, and this we are going to consider it as B. So A dot B the whole bar. What is A dot B the whole bar? A complement plus B complement. What is A here? A bar plus A dot B the whole bar plus B bar plus A dot B the whole bar. Now again we are going to apply the De Morgan's theorem for this term. Here this is considered as A and this A dot B is considered as the second term. So A bar the whole bar will be A and this plus will become dot here. Then A dot B the whole bar. So A dot B the whole bar plus, here also B bar the whole bar. So that will be B bar dot, then A dot B the whole bar. A dot B the whole bar. Now we are going to multiply. Again we are going to apply the De Morgan's theorem here. So A as it is we are writing A, and A dot B the whole bar is what? A bar plus B bar plus this B we are writing here B, and for A dot B the whole bar it is A bar plus B bar. Now we are going to multiply this A dot A bar plus A dot B bar plus B dot A bar plus B dot B bar. What is A dot A bar? It is 0. So and this will become A B bar plus B dot B bar is 0. So we'll get B dot A bar. So finally we are getting Y is equal to A B bar plus A bar B, which is same as the XOR gate operation. Next is implementation of XNOR gate using NAND gates. Actually, we'll get XNOR gate by connecting a NOT gate at the output of XOR gate. So till here it is XOR gate circuit, XOR gate using NAND gates, and at the output we need to connect one NOT gate using NAND gates. How will get NOT gate using NAND gates? If you are shorting the inputs of a NAND gate, it is going to act as a NOT gate. So till here it is same as XOR gate, and the output is inverted using a NOT gate. So this is the circuit diagram of XNOR gate using the NAND gates. So now we are going to see how to implement the logic gates using only NOR gates. So in that the first one is NOT gate. That means we are going to see how to implement NOT gate using the NOR gates. So this is the circuit diagram of NOT gate using NOR gates. The two input NOR gate inputs are connected together and giving only single input A. So the output will be the complement of input A. So here the inputs are same A and A because we are giving common input. And what is the operation of NOR gate? A plus B the whole bar. Both the inputs are added and then the complement. So here the inputs are same. So A plus A the whole bar. What is A plus A? A plus A is A. So A bar. So Y is equal to A bar we are getting. That is nothing but NOT gate operation. So if the inputs are shorted together and giving single input, then this NOR gate is going to work as NOT gate. Next is OR gate using NOR gates. This is the circuit diagram of OR gate using NOR gates. We are using two NOR gates here. To the first NOR gate, we are giving inputs A and B. Then the output of this NOR gate is connected to one NOR gate with input shorted, which is going to work as a NOT gate. So the output of first NOR gate will be A plus B the whole bar, and that is given to this NOR gate input shorted, which is going to act as a NOT gate. So the output will be A plus B complement the whole complement. A plus B complement the whole complement will be A plus B. So Y is equal to A plus B is nothing but the operation of OR gate. So this is the circuit diagram of OR gate using the NOR gates. Next is AND gate using NOR gates. This is the circuit diagram of AND gate using NOR gates. Three NOR gates we are using here. To the first NOR gate, inputs are shorted and giving input A. Second NOR gates also inputs are shorted and giving single input B. That means these two NOR gates are going to work as NOT gates actually, and the outputs of these two NOR gates are given to the third NOR gate. So here the input is A, so output will be A bar. Here the input is B, output will be B bar. Now A bar and B bar we are giving to this NOR gate, and NOR gate operation is what? Addition and then complement. So that means inputs are A bar and B bar. So A bar plus B bar the whole bar. Now what is A bar plus B bar the whole bar? We can apply De Morgan's theorem. A plus B the whole bar is what? A complement into B complement. Here in place of A, it is A bar. So we'll get it as A bar the whole bar into, in place of B, it is B bar actually. So B bar the whole bar. What is A bar the whole bar? It is A into B bar the whole bar is B. So we are getting Y is equal to A dot B. This is the operation of AND gate. So we are getting AND gate operation using NOR gates. Next is NAND gate. As we know, NAND gate is what? It is a combination of and NOT gate. So till here it is same as circuit diagram of AND gate using NOR gates, and output of AND gate we are connecting to one NOT gate. So this is NOT gate using NOR gate, inputs are shorted, so the output will be A dot B the whole bar. Till here it is A dot B, then it is complemented using NOT gate using NOR gate, so output will be A dot B the whole bar. So this is the operation of NAND gate using the NOR gates. So next is XOR gate using the NOR gates. This is the circuit diagram, implementation of XOR gate using the NOR gates. So here also step by step, if you analyze the circuit applying the De Morgan's theorem, at the end we can see the function is given as Y is equal to A bar into B plus A B bar, which is same as the XOR gate operation. Next is XNOR gate using the NOR gates, and we already know that XNOR gate can be obtained by connecting a NOT gate at the output of XOR gate. So here we already discussed XOR gate using the NOR gates. So the same circuit we are taking here. So till here it is XOR gate, and at the output of XOR gate we are connecting one NOT gate. NOT gate means NOT gate using the NOR gates. So this will become the XNOR gate using the NOR gate circuit. Now, if we examine the circuit, at the output we can observe two NOT gates connected back to back. So, if two NOT gates are connected back to back, the effect will be cancelled out. How it is getting cancelled out? See here, we are connecting two NOT gates here and giving one input A. So, output of the first NOT gate will be A bar. That A bar is given to one more NOT gate. So, the output will be A bar the whole bar, which is same as A. So the output is same as the input. So there is no effect of connecting two NOT gates together. So that is how here also these two NOT gates effects will be cancelled. That means the XNOR gate circuit using the NOR gates will be from here to here. That means using only 1, 2, 3, 4 NOR gates. So this is the circuit diagram for XNOR gate using the NOR gates.